So, for instance, Tito, Diego, Adriana, they're not there.
I see.
They didn't want to join.
We did, but
The offer was not very.
the space was not that fantastic.
Come all here, you all four will share this room. It was not like big trouble with office space.
Really?
Yeah. I mean, most offices there are shared.
I see. It looks like there's a mountain, so much room.
They are planning to build a new building. Yeah, the plan is approved, the money is there, so they should start.
Is it above building C?
Yeah, no, above building D.
Okay.
Where the parking lot is, I think it's somewhere in there. Which is trouble because we will lose some parking.
Maybe a problem as well.
Yeah, because we're far, so most people, if you have a car, you take your car to come in. It's only you that come. Not public transport.
Not to the metro, no, but not all the way to the metro. Something more frequent, only going to Grecia and the other stops.
Oh, okay, just here.
So we're streaming this conversation. Live, yes.
It's very interesting, I'm sure.
Good. So, thanks everyone for coming to the seminar. We're really happy to have Vera Roshchina from she will talk about convex sets. So thank you.
Thank you. Thank you very much, Roberto, for inviting me here. So, my first time to give a talk here. I'm a little bit concerned because I'm meeting all of you except Roberto for the first time, except for Juan Pablo also. And I'm not sure what your area is, so please feel free to stop me or ask questions or comments or correct mistakes. So I'm going to talk about something that I'm very interested in, convex geometry. And convex geometry describing certain properties of convex sets in terms of faces of convex sets and arrangements of faces of convex sets. And I will start gentle somehow, and I will start with polyhedral sets and polytopes, faces of polyhedral sets and polytopes. I will mention some open problems. Maybe for some of you, there will be well-known open problems, so be patient in that case. I will move on to something more complicated. And then I will show more open problems, and then I will talk about my research, which is about characterizing very particular properties of faces of convex sets. Okay, so let's start with polyhedral sets and polytopes. Everybody knows what a polytope is, right? So what a polyhedral set is, so you can define a polyhedral set as the intersection of finitely many linear inequalities, right? And the polytope is a bounded polyhedral set or a convex hull of finitely many points. So here on this picture you see the most kind of familiar three-dimensional polytopes: tetrahedron, cube, octahedron, icosahedron, dodecahedron, platonic solids, right? And then when we talk about polytopes, especially when we talk about polytopes in 2 or 3 dimensions, it's very easy to see what are the structural elements of a polytope are, right? Vertices, edges, facets, and so on, right? So we can go to higher dimensions. And also for polytopes, those structural elements can be defined through intersections with supporting hyperplanes, right? So if I have any kind of polyhedral set of polytope, like here you can see a tetrahedron or even a square in a plane or something like this, then I can think about all possible supporting hyperplanes, and those supporting hyperplanes, they cut off those elements of this set, right? And those elements are the faces of the set. So very simple idea, which doesn't fully work for general convex sets, right? Okay. So now I would like to remind you right? About some important questions that are still unresolved. And those important questions are important for optimization, combinatorics, and many fields, right? It's one of the most important open problems that relate to the phases of polyhedral sets. So if we think about edge paths connecting points of a polytope, connecting vertices of a polytope, for example, again, if you take a square and you take any two vertices of the square, then you can see that, well, there's some kind of a choice of two vertices which are at the farthest distance from each other, and you have a two edge path connecting them. So that's somehow the bound for the shortest path connecting two vertices of a square is 2, right? And you look at the cube, and then, of course, you will pick vertices which are really opposite this main, maybe diagonal, and then your path will be 3. So you may know that there was a conjecture called Roshchina conjecture that said that if you have a polyhedral set defined by n inequalities, so you have n facets, and this set had dimension d, that n minus d should be the bound for the shortest path, right, connecting it to vertices. And you see that it's realized on the square and on the cube, right? So that particular statement was disproved in 2012 by Francisco Santos, who found the counterexample to the Roshchina conjecture. And the counterexample is non-trivial because the counterexample, the original counterexample, it lives in a space of dimension 43. It has 86 inequalities. But it's not like he came up with a counterexample in 43 dimensions. He has some kind of a reduction. So he first constructed a set in 4 dimensions that had special properties, and then he transformed it into a 43-dimensional example. And he violated this bound by 1. So he has, in his example, he has n equals 86, d equals 43, and then the diameter, like the edge path, is greater or equal to 44. So, on the other hand, we have some bounds, right? So we have some bounds which are not polynomial. We have quasi-polynomial bounds. There's all sorts of different bounds, right? But this one is probably the most recent one by Mike Todd, and also it's a very nice paper, very easy to read. And we have bounds like this, linear in fixed dimension, but we don't have a polynomial bound. So we know it's not n minus d, but we don't know, right, what is the actual bound. And the relation to optimization is, of course, the simplex method, right, and linear programming problems, because we still don't know if it's possible to somehow construct a version of a simplex method that has a nice worst-case complexity, polynomial worst-case complexity. And then if you think about the simplex method, right, we will be walking along the edges. And if mathematically somebody proves that you can't do better than this, for example, then there's no hope for polynomial simplex method. Right? So somehow the problems with the geometry of polyhedral sets and polytopes are maybe the quintessential mathematical formulation of some problems that we're facing in optimization. Right? Okay, so things are already very complicated for polytopes. And I would like to show you a problem that I like very much, that is still an unsolved problem. That is much easier, it looks much easier than the polynomial Roshchina conjecture. So it's about non-overlapping unfoldings, right? So if you have polyhedral set or polytope in 3 dimensions, you can think about it as of a cardboard box, right? So you can cut it along the edges and unfold it, and that's how we kind of assemble cardboard boxes, right? So I take a cube, I cut it somehow, maybe like this, like that, and then I will have something like this. Right? So I unfold a cube. And of course, for a cube, it doesn't matter. No matter how you cut it, no matter how you unfold it, no matter what net of this cube you consider, it's always consistent. So you can consistently do it, this continuous net, right, and then fold it back into a cube. But it doesn't always work. So if you're not careful, you may not obtain a non-overlapping unfolding, right? So you can see here, there's a truncated tetrahedron. It's a tetrahedron which had its top chopped off and squished a little bit. So here you can see an unfolding that is non-overlapping. So it's a very nice unfolding. You cut it out of a piece of paper and fold it back in. You get your truncated tetrahedron. But this one is not, right? So if you're not careful about cutting it, right, you can't actually cut out of the paper. Okay. And the conjecture, which is called after the German painter Albrecht Dürer, says that every convex polytope has a non-overlapping unfolding. And that's already interesting in 3 dimensions. So the conjecture is an open question in 3 dimensions.
So what would be in the 5th dimension? 4th dimension, when you unfold 3?
Sorry?
When you unfold something which is in dimension 4.
Yes. Yes, exactly. Yes. So if you have a 4-dimensional cube, then you will have in 3 dimensions something like, faces, 3-dimensional faces sticking together in some kind of arrangement. Yeah. So, but the conjecture is open in 3D, so we don't know. And perhaps the most interesting result is this recent-ish paper by Mohammed Gomi. And this paper says that if you take any polytope, you can always apply an affine stretching. You can always stretch it so that you can unfold it, right? In a non-overlapping way. So right, you have.
What is a stretching?
Huh?
What is a stretching?
So just apply a linear transformation.
Linear, not diagonal. It's not just blowing up because this.
No, it's just a linear transformation. But yeah. Yeah, but I'm not entirely sure actually what kind of transformation that is because I wasn't thinking about higher than 3 dimensions. Okay, so that's perhaps enough for warm up about polyhedral sets, right? And some open questions on polyhedral sets. So I'm going to move on to general convex sets and talk about faces of general convex sets. But before I do this, I find this really fascinating that so the conjecture wasn't conjectured by Dürer himself, right? We know that there were conjectures which come from a very long time ago, but this is not his conjecture. However, it was called after him, and you can find this in this publication. It was called after him because he actually studied nets of polytopes and unfoldings of polytopes. So there's a book written by him in 1525 that is, of course, openly available on Google. You can download it. Libraries don't need to subscribe to books published in the 16th century. And it's a lovely book. I mean, it's written in German, and I guess some old version of German, so it's impossible to read for me. But the pictures are really nice. So there's very nice unfoldings of different polytopes. So it's very nice that this conjecture was called after him. Okay. So let's think about faces of convex sets. So as I said before, there's a bit of a complication. So you cannot any longer define a face of a convex set as an intersection with a supporting hyperplane because of the issue with exposed faces. So I will show you this in a moment. And for now, let's look at the definition. So the definition of a face says that a convex subset F of a convex set C is a face if for any line segment that you pick from the set C, right? So the line segment should be in its entirety in the set C. And if you have an interior intersection of this line segment with the subset F, you have to have the whole line segment in the set F, right? So that's the definition of a face. And I think you have to get used to it. If you don't work with this definition of the face, it's actually quite straightforward and really useful for proofs. So, so for example, if I take a cube again, not a cube, square, and then I think about some subset of a square like this, right? It's not a face. can see it here also, similar on a tetrahedron, because if I take any line segment from the set C, or some line segment from the set C, it has an interior intersection, but it's not in the set, so it's not a face, right? Likewise, it has to be a convex set, so something non-convex is not a face. But then you can see that if we apply this definition for our standard faces, vertices, for vertices it holds trivially. There's no line segments inside the set C. For edges, you have to have this line segment right inside the edge. And for faces like this, two-dimensional faces, sorry, or facets, again, you see that, well, the only way for a line segment that intersects this face at an interior point is to actually be inside the face. All right, so for polyhedral sets, we can use both definitions interchangeably. They mean exactly the same thing. But for convex sets, it's a little bit more complicated, so we have to use the second definition. Now let's look at some faces of convex sets. I hope I'm not going through something that is too trivial. Is it too trivial? Is it okay? Okay. So let's look at some examples of faces. So for example, if I take the Euclidean ball, right, then by definition, the Euclidean ball itself will be its face, and then we'll have faces on the boundary. So every individual point on the boundary will be a face, right? Then, well, we studied tetrahedron in detail, so we know that vertices, edges, facets, and the tetrahedron itself are all the faces of the tetrahedron. Here I have a sphere cut in half, so I have a two-dimensional face. Then I have one-dimensional faces on the boundary and the object itself, and this object has 0, 1, and 3-dimensional faces. And also, we usually consider the empty set as a face for consistency, and sometimes we say that it has dimension -1, but it's not very interesting for, not related to this talk. Okay, and now this is the reason why we can't define faces for convex sets in the same way as we define faces for polyhedral sets. That's because faces may not be exposed. So generally what you want is you want a face of a face to be a face. Right? So if you take a convex set, then you take the face of this convex set and you consider all the faces. They should also be the faces of the original object. It's consistent, it's convenient, right? So, and here you can see that if we define the face in the same way as for polyhedral sets, then this point will be missing. This point is not going to be a face because there's no way to expose this face, this point, by line, right, or by a supporting hyperplane. You'll always have this face included as well, right? So that's why we use this definition of faces. Okay, so now I'm going to talk about a small research project that generated some open problems, some additional open problems. So what we wanted to do, it's a project that I did together with David Yost from Federation University Australia and my student Tian-san, who has graduated already. So what we wanted to do is we wanted to see what dimensions of faces of convex sets are possible. Right? So David worked on polyhedral sets, and of course if we have a polytope in dimension D, then you have all dimensions of faces. So you start from vertices 0, then edges 1, and so on. So you have the complete sequence. But you can see already from those pictures that you can have all sorts of combinations for general convex sets. Right? So here I just write down the dimensions of faces. So remember, for Euclidean ball, we have faces of dimension 0, and the whole ball itself of dimension n, right? So 0, 3. Everything for polyhedral set, something like this for a set like this, and a sequence like this for a set like this, right? So, okay. So now the question is to go further, right? So things were very clear for us in 3 dimensions. We wanted to see what happens in 4 dimensions. Right? Can we write down all possible examples? So we write down a sequence of integers, and is there a convex set that has precisely those dimensions? Okay, so, and the answer to this is positive. Yes, it's possible. And in fact, once we've done 4 dimensions, we found a proof that is a proof by induction. right? So I will show you the proof. It's very simple. So just to reiterate, and also to provide additional motivation, right? So for a D polytope of dimension D, the dimensions of faces go like this, 0, 1, 2, and so on D. Don't miss anything. The Euclidean ball is an extreme example, right? It's just 0 and D. And a very interesting example is the cone of symmetric positive semi-definite matrices, right? So you think of those positive semi-definite matrices as a subset of the space of symmetric matrices, right? And they are a very interesting object, of course, for convex analysis. They are even a more interesting object for optimization, right? But for convex analysis, it's a very beautiful object because every face of that cone, of that set, is a smaller dimensional cone of positive semi-definite matrices, right? And the true dimension of a cone of positive semi-definite matrices, or of a space of positive semi-definite matrices, because they are symmetric, right, is like this: D times D plus 1 over 2. So you throw away everything under the diagonal. And then the faces of this cone, they go in those very particular numbers, right? Dimensions, and the gaps increase. The larger is the cone. So again, what finite subsets of non-negative integers can be realized at the dimensions of faces of a convex set? As I said, everything is possible, and we have a proof by induction. So if you write down a sequence, the sequence starts from 0, right? So I want to think about perhaps compact convex sets. Right? So if your sequence doesn't start with 0, if it starts with 1 or 2, then you know that the set is not going to have any vertices. So you can't think of a compact set. So, okay, so suppose that I'm given this kind of sequence. So what I'm going to do, I'm going to first construct a set that corresponds to the first part of the sequence, to the first k numbers, and then we'll combine the set with the Euclidean ball to get the whole sequence. And it works exactly like in this picture. So first of all, we have our induction base. We know what happens in dimension 2, 3, right? We know everything in low dimensions. And then we observe that if we compute the Minkowski sum of, say, a line segment here in this example with the Euclidean ball, then what we have in the resulting object, we have all faces of this Euclidean ball, which is 0-dimensional. The object itself will be 3-dimensional. And then on the boundary, in this case, we'll have copies of, say, this line segment. So we get copies of faces. And you can think about more complicated objects, of course. You add a lower dimensional object to Euclidean ball. You replicate the faces of that original object on what you get there, right? And then you add an extra dimension because you added the Euclidean ball. So that's the inductive proof. And then if the sequence doesn't start from 0, then we can just shift it. So, right, it starts from 3. So we shift it by 3 so that it starts from 0. We construct a compact convex set, and then we add a linear subspace, so to shift it back.
So the set here is constructed as just a set of A plus B, such that A is in the segment and B is in the shift, right?
Mm-hmm.
So how you define that?
Okay. Yeah, so this is Minkowski sum.
Minkowski sum.
Yeah, this is Minkowski sum. Yes, so I should have written it here. So A plus B. Right, and right, and if I can think about something more complicated. So, for example, I take a square, right, and I add a square to a Euclidean ball, and then the object that I will get will look very funny. So it will have, it will replicate the square, right, and then will be kind of round here, like this. So, in fact, these guys will be pieces of this Euclidean ball, right, on the sides, and there will be faces that are copies of the faces of the square, but you see that we don't generate anything new in terms of dimensions, right? Okay. Okay, so fair enough, but this is not the most interesting problem. This is in fact the least interesting problem out of all problems you can formulate about dimensions of faces. The interesting problem is to take some sort of structure, additional structure on the convex set, and then ask the same question, right? So maybe, can you find a convex set that is facially exposed that has this property? Can you find a basic semi-algebraic convex set, and so on, right? So there's more interesting questions than this one. And out of all those questions, the key question is to do it for sets called Spectrahedra, right, which correspond to the domains of semi-definite programming problems, right? So, just as a reminder, right? So one thing is to think about the cone of positive semi-definite matrices, but a much more interesting object, or a whole family of objects, is what you get if you intersect that cone with linear subspaces of different dimensions. Right? So you take a high-dimensional cone, intersect it with a linear subspace, and you can get very complicated sets. Right? There's a whole research field dealing with those sets. So this is a very simple example, right? An intersection of three-dimensional, not three-dimensional, but a cone of positive semi-definite matrices, 3 by 3 positive semi-definite matrices, with a linear subspace that simply restricts, it's not a linear subspace, it's an affine subspace, right? That restricts the diagonal entries to ones. So this kind of objects are called elliptopes. And you can see that there's notation, right? So the matrix should be positive semi-definite. I have restricted the entries, so that gives me my affine subspace. And then the rest of the entries are the variables. So the object will essentially be a three-dimensional object. And you can see why it looks like that. Because you can check the strict inequality. Right? You can check that the matrix is positive definite. So we have X, 1Z, Y, Z1. So you can check that the matrix is positive definite using Sylvester criterion. So you'll take the determinant of this matrix. Right? So we call it M. You take the determinant of M, and that will be 1 minus 2xyz, 1 plus 2xyz minus x squared minus y squared minus z squared, I think. So that should be positive, and then you will check the minor here, so you'll have the determinant of 1x x1, which is 1 minus x squared. That should be positive. So this guy gives kind of funny algebraic variety, right? If you just look at this polynomial and the equality, and then this second inequality chops off this spectrahedron, right? So it's a very nice, spectrahedra have very nice kind of properties, and it's very nice to look at them from the point of view of algebraic geometry. Okay, so the open problem is it true that spectrahedra, which are the intersections of affine subspaces with the cone of positive semi-definite matrices, so you can always think about something like this, right? When you replace the entries of the matrix with some linear or affine functions, right? Have faces in all possible combinations of dimensions. So I think it's a genuinely difficult question because many people looked at it and couldn't solve it. And this question informs some maybe deeper and more important problems in convex optimization. So this is the last big problem I'm going to talk about. And then I will move on to my research. And you will see that there's some motivation coming from those problems that I mentioned. So this generalized Lax conjecture, to me, it's very similar to the Hirsch conjecture and the polynomial Hirsch conjecture about the diameter of polytopes, right? Combinatorial diameter of polytopes that I talked about earlier. Because it's a very algebraic statement, it's a very mathematical statement, but it's also related to practical applications. Because in my primitive understanding of somebody who is doing theory, right, in practice, you have a continuous optimization problem. Perhaps your first attempt is to solve it using linear programming, right? That's really straightforward. If it doesn't work, maybe I can try semi-definite programming problem, right? And if I cannot do it with semi-definite programming, well, I have to do something else, right? So a convex problem becomes really complicated. And of course, a very important question is to see which problems can be formulated as semi-definite programming problems. Right? It's a non-trivial question, and the generalized Lax conjecture is a quintessential question of this kind. Right? So it takes a very specific class of convex sets and asks whether those convex sets can be represented as spectrahedra. Right? And hyperbolicity cones, even though this looks like a complicated definition, they are somehow very natural things. So let me show you some examples, which are trivial examples. So for example, I can have a polynomial like this, xy. This polynomial is a hyperbolic polynomial of degree 2. Right? So it is in 2 variables. It's homogeneous because for homogeneous polynomial, you want every monomial to have the same degree. There's only one monomial, has degree 2, so it's homogeneous. So homogeneous polynomials define kind of homogeneous algebraic varieties, right? So P of xy equals 0 is a cone. So like this, right? You have two lines. Then you want to have some point, E. So in this case, I'm going to pick E equals 1, 1. And for this point, the polynomial P of x minus TE should have real roots. So what I do here is I take x minus t, y minus t, right? And of course, this polynomial has real roots only, right? For if you consider it as a polynomial of t, there's no complex roots, right? And then, so the next step to define a hyperbolicity cone is to look at all points for which the roots are positive, right? So, of course, if x and y are positive, the only 2 roots, they coincide with the coordinates, so they will be positive as well. If x or y are negative, then the roots will be negative. So the hyperbolicity cone that is associated with this polynomial is just a non-negative ortho. And then, so this is a trivial example. Another trivial example is actually the cone of positive semi-definite matrices, because you can think about matrices as variables, and then your polynomial will be the determinant of the matrix. This point E will be the identity matrix, and then you will have the determinant of x minus lambda E, so you'll get the eigenvalues, and you'll get eigenvalues positive, so it will give you a semi-definite cone, right? So, but of course, we know that those trivial examples are hyperbolicity cones, but we don't know the other way around, and it's a difficult problem. So we know certain things about hyperbolicity cones. For example, we know that they are convex cones, which is a fascinating result because you have a completely algebraic definition, and then you prove that those objects are convex. So that's why it's a very nice algebraic object to study the representability problem. You don't need to check convexity. We know a few things about the variety of that hyperbolic polynomial. We know somehow what it looks like topologically. It's kind of shells. We know that those cones are always facially exposed, and a few more things. So the conjecture was proved in 2007 by Helton and Vinnikov in 3-dimensional case, and it's actually stronger. So somehow if you have a hyperbolicity cone and you have the algebraic variety that corresponds to this hyperbolicity cone, it's somehow explicitly the determinant of the relevant matrix. It's not true in such strong case for high dimensions, but right, the conjecture is still open. There's a lot of recent results, so it will probably be solved soon, but still an open question. Okay, so that's another motivation to study some sort of properties of convex set. And now I'm going to move on to the specific topics that I'm very interested in. And I will talk about facially dual complete or nice cones. So it's a particular property of convex cones. And the motivation comes from making convex problems look better somehow for numerical method, right? So if you look, so this is just a standard convex optimization problem, minimizing a linear function over a linear constraint and some cone, right? So if we think about this feasible domain, then it's a standard way to view it as the slice of this cone, right? It's like the spectrahedra I was talking about before. So for spectrahedra, this guy will be a semi-definite cone, right? But of course, we can consider more general problems. Hyperbolicity cone or any kind of cone, convex cone that is convenient for this particular model or particular problem. So geometrically, if we have this linear space cutting the cone through its interior, then the problem is very nice. Right? So you don't have any problem with numerical methods, you don't have problems with duality, and so on. If this equality, this linear subspace, is touching the cone, then it's problematic. Right? So not touching, so you have maybe something like this, right? So the intersection is not through interior. So one of the ways to deal with this is to reduce this cone to a face. Right? So I just identify a face that has a relative interior intersection with this linear subspace, and then I remove the cone, and I only keep the face. Right? So that's the idea of facial reduction. And it can be somehow implemented in practice. Of course, there's issues with precision, fine precision, and things like this, but it's an actual practical idea. Okay, so now if we do this, then we have a primal problem. Of course, for every primal conic problem, we can write a dual problem. So if I replace this conic constraint with a smaller set, then for a dual problem, I'll have a bigger set. That's the dual to a new constraint. And basically, this constraint here will become something like this. Right? The dual for the original cone intersected with the linear span of the face, which is, it's well known that it's the closure of the sum of the dual cone with the orthogonal complement to the face. So facial dual completeness is a property that says that this guy is closed, so we don't need to take this closure operation. Right? So, and so this is the main motivation for studying facial dual completeness, but it comes up in other applications, in other papers. So it looks like it's a quite an important property, but to me it's just interesting because it's a very difficult property to see geometrically, right? You want to pick every face of the primal cone, and you want the sum of the complement of that face with the dual cone to be closed, right? It's very hard to see what happened. So my goal was to somehow describe it in a more convenient way to get hold of this property. So this is just an advert for facial dual completeness. It's important in duality theory because of facial reduction and other things. There's no exact characterization, and exact characterization means something that is easy to check. So maybe you want to write it down in terms of some polynomial that defines the set or a function that defines the set or something like this. There's no explicit characterization. So the only one is via facial reduction. And it's important for checking the closeness of an image of a convex set under a linear map. And it comes in all sorts of works and just when convex cones and convex sets are studied.
So the advantage of doing the reduction is that we can use a simpler method to solve the optimization problem. Maybe just an LP perhaps? Or?
Sorry?
The advantage of doing the facial reduction is that then we can solve the problem by a simple
Yeah,
method.
yeah, you can solve with well, it may still be so. It's a very fortunate situation when you end up with a polyhedral phase, right? But even if you don't end up with a polyhedral phase, still if you use say an interior point method, it will work much better. Of course, I mean I'm not even sure if you can use an interior point method on a nil-post problem. So you have better duality relations, and you have better performance of numerical methods, right? Because numerically, I mean, you perturb this a little bit, and you don't know whether there is a solution or not, right? So, basic complexity problem. Yeah, so I think when we talk about convex problems, which are non-polyhedral, so when we talk about conic problems like this,
Correct me if I'm wrong, but we have the same doubt. So when you start with your original problem, you don't have Slater condition, whereas when you do the facial reduction, you recover
Yeah.
in this restricted space.
yeah,
Is that the issue?
yeah, that's exactly the thing, yeah. And for some cases, for some particular cases, you can do it almost automatically. So for example, if this is...
The trouble is to identify which phase you want to...
Yeah. But you can somehow do it. So if this is a semi-definite programming problem, for example, there's a result by Pataki that allows you to solve an auxiliary semi-definite problem that tells you the actual reduction, that tells you how to take the cut to reduce the phase. There's some issues with finite precision, so this stuff works for infinite precision, but it still right. It still works and it's still used. So. Sorry. Okay. Okay, so let's look at this property again. So again, this is just a property that I'm personally interested in, that I'm personally fascinated about, but you can see the motivation. So for example, we don't yet know if hyperbolicity cones are facially dual complete or nice, and that was actually the motivation. We want to show using the results that I'm going to talk about whether that the hyperbolicity cones are facially dual complete. So I'm going to write this property. So I want K star, the dual cone, plus F perp to be closed. Right, so of course this dual cone is just such Y. Everything is finite dimensional. That X, Y is greater or equal to 0 for all X and K. And the polar is the negative of this. And then F perp is the linear complement to the face. Right? So it's all such that X, Y is 0 for all X. Yeah. Okay, so this is just a simple illustration. So in 2 dimensions, everything is facially dual complete. So there's never a problem. So what we do, we take a face, construct the orthogonal complement, then take the Minkowski sum of the dual cone or polar cone. Doesn't matter, right? Because the dual cone is negative of the polar. Just easier to draw a polar cone on pictures. And then we want this set, this sum, to be closed. Of course, it's closed in 2 dimensions always. This is the minimal example of a cone that is not facially dual complete. So in this case, it's like that small example that I showed to you before. So you take a disk and then add a corner to this disk, and then homogenize it, right? So I turn it into a cone. So I put it in a plane, in 2-dimensional plane, and then I construct a conic hull. So it's some kind of a cone that has exactly the same facial structure as the set. So there's unexposed faces. And here, if I pick a 2-dimensional face like this, take its orthogonal complement, and add it to the polar cone, to the original cone, this set is not going to be closed. Right? So if you think about the Minkowski sum of this set, this line, with the polar cone, it's like moving the polar cone along this line. There will be a direction here, or even half plane here on this side, that is not part of the sum. Right? So it's not going to be closed. And actually, this particular cone is facially exposed. It's not facially exposed, sorry, right? So it has this problem, facial exposure. And in 3 dimensions, facial exposure is the same as facial dual completeness. And we have another, but it's not true for high dimensions. So for high dimensions, things get more complicated. And there's this Pataki sandwich theorem, which I like very much. It says that a facially dual complete cone is facially exposed. Right? So if you have this property, then you also don't have this problem, right? Every face is exposed. And another one is that if a cone is facially exposed with every properly minimal face, of each dual cone to each face, then the cone is facial dual complete. It looks complicated, but it's actually a very convenient property for proofs, because in a lot of cases you can check facial dual completeness using this property. But there's a massive gap between these two properties, so they're not a characterization. For example, we have four-dimensional convex cone, so this is a slice. So it's exactly the same thing. You can think about a four-dimensional cone and then cut it with a three-dimensional space and then look at what you get, right? Because this cut will look pretty much exactly like the cone, right? The cone, the difference between the set and the cone is just that it's homogenized. So this is an example of a four-dimensional convex cone that is facially exposed but not facial dual complete, right? So it shows that this property is not equivalent to facial exposure, right? So it yields facial exposure, but it doesn't work the other way around. And you've seen on the previous slide this Pataki sandwich, this characterization. It doesn't, of course, describe all possible cases, so there's quite a gap between facial exposure and this property. So we wanted to close this gap. We didn't fully close it, but we made some good progress. So this is joint work with Tangentially from University of Waterloo. So first of all, we have necessary condition. So we know that if our set or our cone is facial dual complete, if the cone is facial dual complete, then not only it's facially exposed, but we have a stronger property. We call it a tangential exposure. So what we have is the tangent cone at any point to the cone itself intersected with the linear span of the face is the same as the tangent cone to the face. So you can see that on that example that I was showing you before, it doesn't happen. Right? So here I have this two-dimensional face of this complicated three-dimensional set. Then the tangent to this face is kind of a quarter of a plane, right, here. And then if I take a tangent to the cone, because there is this direction here, or the tangent to this whole cut of a cone, I get something more, right, in the intersection with the linear span of air. So we were very excited when we found this property, but we discovered that it's only a necessary condition. So you can see that in some examples it doesn't work, but it's only necessary. Okay, so we call this a tangential exposure. And just a reminder that the tangent cone is a standard tangent cone of convex analysis, right? So you just take a convex set, consider a point, and just blow the set up, keeping the point fixed, so you get the tangent cone. Okay. So we found some tangentially exposed cones, so the cones which satisfy our condition, they are not facial dual complete. So again, it's a three-dimensional slice, and we managed to change that original example using a cubic curve here, so that the necessary condition is satisfied, but the cone is not a facial dual complete. It's not a sufficient condition. And what we did is eventually we found a sufficient condition. And there's an interesting relation between the sufficient condition that we found with Nesterov's lexicographic derivatives. So there is an idea by Nesterov that is called the lexicographic derivative. And what you do is you take a function, you compute the directional derivative of this function. Right? So you pick a point, compute the directional derivative. Then this directional derivative in itself is a function. Right? It's a homogeneous function. So then you can compute the directional derivative of the directional derivative at various points, and then you continue like this until you reach a linear function. You will always reach a linear function in steps. So then you collect all those gradients of this linear function, and you get some sort of a lexicographic subdifferential. And it's lexicographic because there's some properties that allow you to go in one direction, then take a step in the orthogonal direction, and so on until you exhaust all directions in n-dimensional space. And we did a geometric equivalent of this thing. So even though it looks ridiculous, it works, and it's it's a very useful way to describe this property. So we take tangents, all possible tangents to our set or to our cone, and then we take all possible tangents of those tangents at all points, and all possible tangents again. So we collect all this massive set of sets, and then we want that property that we had before. We want that property of tangential exposure to work for all tangents. Right? So we want this property that we had in our necessary condition to work for all tangents of all order. And if this happens, then that gives a sufficient condition for facial dual completeness. So there's still a gap, but both conditions are quite constructive because dealing with tangents is quite easy when you have sets defined by polynomials. Right? You pretty much have explicit tangents. So our hope is that we will continue and prove some interesting results about some algebraically defined objects. Okay. So this example shows that our condition is sufficient condition is not necessary. So this cone is not tangentially exposed, but it's facially dual complete. So there's an actual gap. None of those conditions are characterization. And I think the last thing that I want to show you is a very new work by Bruno Lorenzo from the University of Tokyo on amenable cones. So he defined a property that is called amenability. It looks a little bit like an error bound, but it's not. It's a very special property. So you take a closed convex cone, and you say it's amenable if every face of this cone has a constant k, right? So k depends on the face, such that the distance from x to f is less or equal than k distance, right, from x to k, but only for points in the linear span of the face. So it's some kind of very restricted error bound on regularity property. And he has shown, just as a side kind of result, so it's not the most important result in the paper, that amenable cones are facially dual complete, but we don't know if it works in the opposite direction. We don't know if facially dual complete cones are amenable. And also, we don't know what is the relation between what I did with Levent and what Bruno defined, right? So it's completely unclear what is the relation between amenable cone, strong tangential exposure, and tangential exposure, right? So, but also it's not the main thing in this paper. So he's using this very nice property to obtain some error bounds for non-polyhedral cones. It's a very nice paper, which I hope soon will be published. Okay, so that's it. Thank you very much for your attention. Okay.
Derivative of the derivative.
Okay.
I mean, 90. But then there is a dual relation, which is instead of taking the tangent to the tangent, you take parabolic approximations of your set.
Okay.
So instead of just looking at rays that
are
close to your set, you look at parabolas that are close to second order.
This
defines another geometrical object. And there is a very strong relation between this the properties of these second order tangent sets with polyhedricity. And many works in the 70s already on this extended polyhedricity, which were used on PDE problems as far as I remember. So there might be a relation with that, and my question would be, can you hope to have a characterization of this extended, how do you call it?
Facial dual completeness.
In terms of the curvature of your set.
In terms of what?
Curvature.
Or maybe, yes, yes. It's this kind of thing, but we try to capture it. So I mean, your intuition is entirely correct, right? We try to capture it, and for now, the best thing we have is something like this, right? So of course, if somebody manages to get some very explicit representation, even if it's just for semi-algebraic sets, for example, that would be really nice. But we couldn't. So, but it's probably possible, right? Yeah. So it's precisely the key, the relation between curvatures, right? Yeah.
Can you give me some maybe graphic intuition that the last cones, how they look like? Yeah, the one that's satisfied.
This one?
Yeah.
Okay, so maybe let's take just a set, because the property, I guess, can be done for a set. So maybe I have something like this. Let's say I have this flat face here, and then the remaining set is maybe like this, right? Or let me call it C. So then I have to check this property only for the linear span of F, which for convex sets will be the affine span, right? So I will take the plane that is spanned by this face.
But C is a cone.
Yeah, so think about a slice of a cone, right? So because it's hard to think of cones, it will be maybe an ugly picture. Maybe you can also take a cone. So take a cone. Maybe here you have something non-polyhedral, right? Maybe this is a face of the cone, right? Then you take the linear span of this face, right? So take the linear span of this face, and then you want to have this constant so that the distance from every point in span F to the face is less or equal than k distance from x to k, right? So you approach this face, but you stay within this plane, right? So basically what will happen if your cone is somehow approaching the face tangentially, then there's a problem with this property, right? So if you have the face here, you have this plane, right? And your cone is kind of here, right? You break this property because the distance, so if you look at the distance from points, you take a sequence of points like this, you look at the distance to this cone and compare to the distance to the face, right? So this guy will be much larger than this one, so you wouldn't be able to get a constant. So it's very similar to facial exposure, but it's somehow stronger. Right, so if it tells you basically that if you have a face and then you have the rest of the set, it shouldn't be tangential. It should really come at some angle.
So there's no kappa because you can go as far as you want, and then this distance will the difference get as large as possible.
So I think the problem will usually happen close to the set.
But if it's so close, then I could get like a large kappa. So.
Yeah, but it still wouldn't. The problem is like this, right? So if this is my F, this is my cone, right? So think it's really tangential here, and then I pick points here on this line, right? So this is my distance to the cone, this is my distance to the set, and this distance gets smaller much faster than this distance, right? So you wouldn't get a linear relation. You'll probably get some quadratic relation or something like this. Yeah. So personally, I think it's a very nice property. So, even though it's yeah. And not much is known about it because it was just introduced and the paper is still not published. But I think it's a very nice paper also because it uses this property for many interesting things. Right? So to me, the property itself is interesting enough, but.
Thank you very much.
Okay, thank you.